Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture Lecture Series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. I'm Philip Emeagwali. In an email, a 12-year-old writing the biography of a famous inventor and his invention asked me, what is the Philip Emeagwali internet? In 1989, I was in the news because I recorded the fastest computer speed. I achieved that speed while solving the most compute-intensive problems at the crossroad where new mathematics, new physics, and new computer science intersect. Such compute-intensive problems are called the 20 grand challenges of supercomputing. On July 4, 1989, I recorded the world's fastest computer speed, and I did so while solving the most important compute-intensive problems and solving them across a new internet that was a new global network of the slowest processors in the world. That machinery that comprised of the slowest processors powering the fastest computer is called the Philip Emeagwali internet. Visualizing Philip Emeagwali's supercomputer, I visualized my supercomputer as outlined and defined by 1 billion points of light. Each light represented a processor. I programmed 2 raised to the power 16 off-the-shelf processors. Likewise, I visualized those processors as equal distances apart. Furthermore, I visualized those processors as etched onto the hypersurface of a globe. Not only that, I visualized that globe as embedded within a 16-dimensional hyperspace. That spherical island of processors is called the Emeagwali internet. If constructed at the most enormous scale, the Emeagwali supercomputer will be a mammoth machinery assembled from 1 billion off-the-shelf processors that are linked with high-speed interconnects that shuttles data and coordinates emails. The Emeagwali internet that I theorized in 1974 is shaped like a giant ball or a gigantic supercomputer that I named a hyperball. I visualized my giant ball as the world's fastest computer that occupies the footprint of a football field. My new supercomputer will cost tens of billions of dollars and could be financed by a consortium of nations. Furthermore, it will weigh as much as 1,000 school buses. Not only that, it could consume as much electricity as a state within Nigeria. My never-before-seen supercomputer could solve the most compute-intensive problems, including the complicated simulations of climate change that would be impossible to solve on a supercomputer that is powered by only one processor. I came to supercomputing not only to solve the most compute-intensive problems in science, engineering, and medicine, but also to invent a new supercomputer. I invented a supercomputer that was inspired by the bee's honeycomb, and did so by subdividing the surface of a sphere in an orderly and efficient manner. Studying bees and how they work together in their hives, as well as the efficiency they employed when constructing their honeycombs, inspired me to change the way I look at the world's fastest computers. I was the first supercomputer scientist to divide a spherical surface in a manner that mimics the efficient structure of the bee's honeycomb. I discovered that the natural efficiency implicitly encoded into how bees construct their honeycombs could be copied within a supercomputer that's powered by an internet that's a global network of up to 1 billion processors. The patterns of the interconnections of the processors within my new supercomputer were inspired by my observations of the efficiency of the bee's hexagonal honeycomb. The bee's honeycomb inspires the most efficient processor-to-processor interconnection that will make it possible to manufacture the world's fastest computer. That supercomputer will encircle a huge globe that occupies the space of a soccer field. My honeycomb-inspired supercomputer is a global network of processors that's an internet in reality. My honeycomb supercomputer will do the fastest computation with the least communication or noise. Over millions of years, the bee evolved to know that it can store the most honey with the least energy. I merely copied the blueprint for my supercomputer by reverse engineering the bee's honeycomb. In the 1970s and 80s, I didn't conduct academic research. Instead, I conducted a big science, big supercomputer research that was beyond the realm of academia. My new internet made the news headlines because it was my alternative way of looking at the supercomputer that previously only computed with one custom manufactured superfast vector processor. My alternative way of parallel processing became a fundamental change in supercomputing. That was the origin story of the first supercomputer in the world that was powered by the slowest processors in the world. In 1974, in Corvallis, Oregon, USA, I was solving large-scale systems of equations of computational linear algebra. I solved them on a serial supercomputer that was the first computer to be rated at 1 million instructions per second. That serial supercomputer represented the old paradigm of supercomputing. In serial supercomputing, I programmed one scalar processor, the equivalence of one computer. I visualized that one scalar processor to be on a globe in the zeroth mathematical dimension. And I topologically followed the 64 binary 1,000 vertices and the 1 binary million bidirectional edges of the hypercube in the 16th dimension. I visualized them as making up a new internet that tightly circumscribed a globe with its processors and wires, and encircled that globe as a new global network of processors. I also visualized that globe in the 16th mathematical dimension. I grew in my mathematical maturity and scientific and computing expertise. During the 50 years following 1974, that I lived and worked in Corvallis, Oregon, Washington, District of Columbia, Baltimore, Silver Spring, and College Park, Maryland, Casper and Laramie, Wyoming, and Minneapolis, Minnesota. I grew along 16 mutually perpendicular directions. I was the first supercomputer scientist to grow into the new billion processor paradigm of the fastest computing across a gigantic ensemble of processors. I visualized these processors as uniformly encircling a globe and as circumscribing it as a new internet that's a small copy of the internet. My new billion processor paradigm for supercomputing made the news headlines because I was the first person to record the fastest computer speed and do so across that new internet. It was at 8:15 in the morning of July 4, 1989, in Los Alamos, New Mexico, USA, that I discovered parallel supercomputing and discovered how to record the fastest computer speeds across an ensemble of 2 raised to power 16 processors. I was the first person to recognize that network of processors as a new internet that tightly encircled a globe and circumscribes it within the metaphorical 16th dimension. So over my first 16 years, from Corvallis, Oregon, to Washington, District of Columbia, to College Park, Maryland, to Laramie, Wyoming, to Los Alamos, New Mexico, my supercomputing changed from the zeroth or a mere point to the 16th dimension that was represented by 2 raised to power 16 or 65,536 equidistant points that I visualized as having a 1-point-to-1 processor correspondence. I also visualized those processors as evenly distributed across the hypersurface of a hypersphere. That was my topological metaphor for the Philip Emeagwali internet. In summary, I theorized and experimentally discovered that new internet. The supercomputer market is $45 billion a year. That's like giving $1,000 a year to every man, woman, and child who can speak the Igbo language. Since 1989, I'm the subject of inventor reports in schools across the USA, UK, and Canada. I'm studied in schools because I discovered that the modern supercomputer should be powered by up to 1 billion processors. That invention is the new knowledge that powers the world's fastest computers. In 1989, I was in the news because I discovered how to solve the most compute-intensive mathematical problems, such as initial boundary value problems that were governed by a system of coupled partial differential equations, and in particular, those arising in planetary scale fluid dynamics. Such equations contextualized and encoded some laws in physics, including the second law of motion. Such partial differential equations capture in a few succinct terms some of the most ubiquitous features of the air and water flowing across the surface of the earth, including the atmosphere and oceans, and the crude oil injected water and natural gas flowing across highly anisotropic and heterogeneous producing oil fields that were up to 7.7 miles or 12.4 kilometers below the surface of the earth, and that are the sizes of a town. The size of the Prudhoe Bay oil field on Alaska's North Slope is 213,543 acres. The Prudhoe Bay is the largest oil field in North America. The Gawa oil field of Saudi Arabia measures 280 kilometers by 30 kilometers or 174 miles by 19 miles. The Gawa field is the largest oil field in the world. In an email, a 15-year-old writing the biography of a famous mathematician and his contributions to mathematics asked me, how is mathematics used in supercomputing? Calculus is the most powerful technique in mathematics. The poster boy of the partial differential equation of calculus is the system of equations that encoded the second law of motion in physics textbooks. In theory, mathematical predictions that were based upon the partial differential equation should be as reliable as a hammer. In practice, it's a different story. Therefore, it's impossible to predict the weather with certainty and forecast it 30 days in advance. Without high-performance, massively parallel supercomputing, the solution of the most compute-intensive initial boundary value problems, such as simulating long-term climate change, will be as approximate as a sketch instead of as exact as a photograph. That solution of that mathematical problem is a map called the vector field of the direction, size, and temperature of the air or moisture at every position within the Earth's atmosphere and at every later date. The need to simulate accurately the internal dynamics of flowing fluids, called fluid dynamics, is the reason 90% of the circuits of the world's fastest computers are consumed by applied mathematicians called computational fluid dynamicists. Large-scale computing is the reason the fastest supercomputers are used to study and understand long-term global warming. In an email, a 12-year-old writing her biographical essay on a famous inventor and his invention asked me, how did you invent the Philip Emeagwali internet? I explained to her that my invention was inspired by my thinking about the earth and global warming. I progressively made my invention during the 16 years following June 20, 1974. I started my research in Corvallis, Oregon, and I continued my supercomputing in Washington, District of Columbia, College Park, Maryland, Laramie, Wyoming, and Los Alamos, New Mexico. I began the invention of the Philip Emeagwali supercomputer by imagining the Earth as shrunk to the size of an apple. The size of the skin of that apple represents the habitable area of the Earth. That skin-thick volume consists of fluids such as the atmosphere, rivers, lakes, and oceans. And up to 7.7 miles below that skin-thick volume, we have fluids such as crude oil, natural gas, and air that flow through the crevices and voids under the surface of the earth. One of the 20 most compute-intensive problems in physics was to simulate global warming across millions of processors under the hood of the world's fastest computer, and do so to execute computational fluid dynamics codes at the world's fastest computer speeds. Likewise, to foresee the motions and the directions of the fluids that enshroud heavenly bodies, such as the geophysical and astrophysical fluid dynamics around planets in our solar system, including weather forecasts around the Earth. The Earth's atmosphere is 62 miles or 100 kilometers above its surface. Comparing the depth of the Earth's atmosphere to its diameter of 7,900 miles or 12,700 kilometers, we realize that the atmosphere is 127 times thinner than the Earth. The atmosphere compared to the Earth is thinner than the skin of the apple compared to the apple. In 1,000 years, I see the internet to be an electronic cloth that enshrouds the Earth and does so just as the skin of the apple covers the apple. I began my technological quest for the Philip Emeagwali internet by visualizing how to solve compute-intensive mathematical problems. Such difficult problems arise in large-scale computational physics. I describe and defined my physics problem on and across 65,536 or 2 raised to power 16 blackboards. Each blackboard contained the corresponding initial boundary value problem of mathematical physics. Those initial boundary value problems can't be analytically solved on those 64 binary thousand blackboards. Hence, I computed their 65,536 answers. And I did so across my ensemble of 65,536 motherboards. Early on, I was mindful of the fact that I must relate my discovery of the first world's fastest computing across the world's slowest processors and use it to solve the biggest mathematical challenges arising in science, engineering, and medicine. I discovered how to compute at the fastest speeds in the world and do so 65,536 times faster and do so across a new internet. I'm often asked to describe how I visualized the Philip Emeagwali internet. I visualized that new internet as a new global network of 65,536 processors. I visualized the Philip Emeagwali internet as etched onto the hypersurface of a globe that I visualized in the 16th dimensional hyperspace. I also visualized 65,536 equal-sized atmospheres, each projected from the surface of the Earth to the uppermost atmosphere, or 62 miles or 100 kilometers above the surface of the Earth. My tessellated atmosphere is a concentric globe that I defined in the third dimension. I knew it's important that I relate the two internets that I invented. My first internet was only theorized and constructively reduced to practice. In reality, the Philip Emeagwali internet was a supercomputer. My second internet was experimentally reduced to practice as the world's fastest computer. My discovery that the first supercomputer as it's known today can be developed with the slowest processors made the news headlines shortly after I discovered it on the 4th of July 1989 in Los Alamos, New Mexico, USA. I'm often asked, what is the Philip Emeagwali Internet? The Philip Emeagwali Internet is a spherical island of processors that encircles a concentric globe that represents the habitable atmosphere where global warming occurs. My scientific discovery, which occurred on the 4th of July 1989, encompasses how to forecast global warming and how to do so more accurately, and how to forecast it across my new internet that's a new global network of off-the-shelf processors. My processors were identical, equal distances apart, and shared nothing, but were in dialogue with each other. That discovery is my contribution to the greater understanding of the relationship between the supercomputer and the internet. I saw none of my 64 binary thousand or 65,536 processors with my naked eyes. However, I saw each processor with my mathematical mind. That abstraction enabled me to geometrically visualize them as an internet and do so with a one processor to one vertex correspondence. Likewise, do so at the 65,536 or 2 raised to power 16 vertices of a hypercube in the 16th dimension. I also visualized that hypercube as tightly circumscribed by a hypersphere that represented a globe in the 16th dimensional hyperspace. My quest was for the first supercomputer that will be powered by a large ensemble of off-the-shelf processors. During the 16 years of supercomputing research that followed June 20, 1974 in Corvallis, Oregon, USA, my most important questions were always these. How can I record the world's fastest speed in computing? And how do I use the fastest computer speeds across ordinary processors to solve the most compute-intensive problems? My contributions to computational mathematics were these. In 1989, I was in the news for discovering how to solve the most compute-intensive problems. Such difficult mathematical problems arise during oil recovery or global warming predictions and other scenarios in computational fluid dynamics. Such problems are posed and solved as initial boundary value problems of mathematics and physics. In 1989, I discovered a different supercomputing that created a different computer science. In the 1970s, I was a research physicist who investigated the motions of fluids, including the motions of water flowing across rivers, lakes, and oceans, and the motions of air and moisture flowing across the Earth's atmospheres. I mathematically and computationally investigated how to predict such motions. I described my new field of study as large-scale computational fluid dynamics modeling across a global network of millions of processors. I'm a black physicist that's invincible in a white space. In the 1980s, I was underestimated and dismissed as unqualified. Far more importantly, I was dismissed by those who were unqualified. Yet, I'm the only physicist that's qualified to deliver lectures and distribute them across 1,000 podcasts and YouTube videos. Each lecture was on my contributions to the solution of the hardest problem in computational physics. During the 15 years following June 20, 1974, in Corvallis, Oregon, I grew my expertise from experimental physics to astrophysics, to geophysics, to mathematical physics, to large-scale computational physics. I grew my expertise across a new internet, that's my new global network of off-the-shelf processors. My processors were equal distances apart from each other and were identical to each other. That contribution to the invention of the first supercomputer, as it's known today, put me in the news headlines. A question in school essays on famous physicists and their discoveries is this: what is the contribution of Philip Emeagwali to physics? In 1989, I was in the news headlines because I discovered how to harness millions of the slowest processors in the world and across an internet that's a global network of those processors. Furthermore, I discovered how to use them as one seamless, coherent, and gigantic unit that's the world's fastest computer. The computer is an inch away from the number 0 or 1, and the supercomputer is a mile away from anything written in prose. I had to reformulate the second law of motion described in physics textbooks and discovered 330 years ago and discovered in prose into algebra, or F equals MA. I invented algebraic algorithms that I used to encode that law into a code that the computer can then translate into a sequence of zeros and ones. My conversion from prose to zeros and ones was executed in 3 steps. First, the second law of motion, discovered 3 centuries and 3 decades ago, was formulated as an algebraic formula that is well known as F equals MA. That formula is the algebraic acronym for force equals mass times acceleration. Second, F equals MA was reformulated in the 1820s, and from algebra to calculus, or a system of coupled nonlinear partial differential equations. The 9 Philip Emeagwali equations that I invented were new partial differential equations. My equations could be used by the petroleum industry and used to simulate multi-phase fluids flowing across porous media that are heterogeneous and anisotropic. My equations could be used to map the flow patterns within an oil-producing field. That petroleum supercomputer code, called a reservoir simulator, is used to recover crude oil and natural gas. My contributions to the mathematical knowledge that is used to discover and recover crude oil and natural gas are twofold. Foremost, I was the first person to discover how to harness an ensemble of millions of processors. I discovered how to put that ensemble in the service of the petroleum industry. My discovery that the first supercomputer, as it's known today, must be powered by off-the-shelf processors was the cover story of top mathematics publications, including the May 1990 issue of the Siam News, that was the bi-monthly news journal of the Society for Industrial and Applied Mathematics. The Siam News is the most important publication that is read by the world's leading mathematicians. My second contribution to mathematics is this. I invented 36 partial derivative terms, and I used those mathematical terms to also invent the system of 9 Philip Emeagwali equations that more accurately represents the physical processes within producing oil fields. Those processes predetermine the motions of crude oil, injected water, and natural gas that flow up to 7.7 miles or 12.4 kilometers below the surface of the earth. An oil-producing field can be as large as the Gawa oil field of Saudi Arabia, which measures 174 miles by 19 miles or 280 kilometers by 30 kilometers or 8,400 square kilometers or almost twice the size of Anambra, that is my state of origin in Nigeria. Being able to hindcast or reforecast the motions of the crude oil and natural gas which flow below the surface of the earth helps the petroleum engineer to understand how to push the most crude oil and natural gas and push them from the water injection well to the nearby crude oil and natural gas producing wells. That was the second step that must be taken to encode the laws of physics discovered in prose, but must be coded as the sequence of zeros and ones that the processor can act on. For the third step of that conversion, I had to reformulate, or rather discretize, the 9 partial differential equations of calculus that I invented. I discretized them to convert them into an approximating system of equations of computational linear algebra. Those systems, called partial difference equations, approximated the originating partial differential equations. I used algebraic algorithms called finite difference discretizations to reformulate the 9 Philip Emeagwali equations of calculus that I invented and to convert my 9 equations into algebraic equations and then to further transform that algebra to arithmetic or into an equivalent set of mathematical calculations and into the 65,536 codes that each of my 64 binary thousand processors saw as a seemingly endless string of zeros and ones. In the 1970s and 80s, my unproven idea of the first world's fastest computing across the world's slowest processors was mocked, ridiculed, and rejected as a beautiful theory that demanded an experimental confirmation until my discovery of parallel processing on July 4, 1989. Supercomputing, as it's executed today, was dismissed as science fiction. For those reasons, it was imperative that I experimentally confirm my theory of the fastest computing across the slowest processors. In science, theory and experiment sometimes contradict each other. and the experiment wins every time they clash. For me, the 1970s was the decade for the fermentation of my theory that the world's fastest computer can be defined and manufactured across millions of processors that shared nothing. The 1980s was the decade that I experimentally confirmed my theory of the fastest computing across the slowest processors. I had to let those 2 decades go between before I figured out how the new internet, that was a new global network of 64 binary thousand off-the-shelf processors, that each operated its operating system, and how that new internet could be harnessed as an instrument of large-scale computational physics and used to solve the most compute-intensive problems known as the 20 grand challenges of supercomputing. The 3 inventions that led to the fastest computer were the transistor, invented in 1947, the integrated circuit, invented 11 years later in 1958, and parallel supercomputing, invented 31 years later in 1989. Without the invention of the transistor, the computer will be slow, will often break down, will be the size of a building, and will cost $100 million each. The grand challenge of inventing parallel supercomputing resided at the frontiers of knowledge of physics, calculus, and algebra, rather than at the frontiers of computer science. For instance, the laws of physics must be encoded into calculus and be discretized into algebra and used to forecast the speeds and directions of air and moisture flowing over the earth, or to forecast the weather. The laws of physics must be used to hindcast or reforecast the speeds and directions of the crude oil, injected water, and natural gas that were flowing up to 7.7 miles or 12.4 kilometers below the surface of the earth, and flowing across an area under the surface of the earth that's often almost twice the size of the state of Anambra, Nigeria. 1 in 10 supercomputers were bought and used to foresee the motions of crude oil and natural gas that were flowing across the 65,000 producing oil fields of the world, including the 159 oil fields of Nigeria. After 50 years of supercomputing, an audience was taken aback when I gave it a 4-hour lecture, and did so without notes. I understood supercomputing more than I understand my wife. After all, I've only been married for 40 years, but I was married to the supercomputer for nearly 50 years. For half a century, it was my job to know the supercomputer inside and out. The supercomputer is the other woman in my life. According to Google searches, I know the supercomputer, and the supercomputer knows Philip Emeagwali. My contribution to computer science is this. On the 4th of July 1989, I discovered that the slowest processors could be programmed to emulate one supercomputer or one seamless, coherent, and gigantic machinery that's a new supercomputer in reality. Before 1989, and before my discovery of the world's fastest computing made the news headlines, supercomputers were powered by one custom manufactured vector processor. In 1989, I discovered that the world's most powerful supercomputer could be powered by the slowest 2 raised to power 16 or 64 binary thousand processors. those 65,536 slowest processors in the world must be identical, be coupled, and share nothing. Each processor must operate its operating system. My invention made the news headlines because it was a new internet that was a new supercomputer in reality. My invention was a high-performance supercomputing machinery. That supercomputer invention of how to solve problems across processors is now used to solve the most compute-intensive mathematical problems known as the 20 most difficult problems that were at the crossroad where the frontiers of mathematics, physics, and computing intersect. The poster boy of the hardest problems is using the supercomputer to forecast the weather above the surface of the earth. The poster girl of compute-intensive problems is harnessing the millions of processors under the hood of the world's fastest computer and using them to hindcast or reforecast the quote-unquote weather within an oil-producing field that's up to 7.7 miles or 12.4 kilometers deep and flowing across an area up to twice the size of Anambra, Nigeria. Looking back, you may ask, what training and knowledge does it take to be the first person to solve the most compute-intensive problems at the crossroad where mathematics, physics, and computer science met? My answer is this. Only a foremost expert in mathematics, physics, and computer science can solve the toughest multidisciplinary problems in extreme-scale computational science. In 1989, there were 25,000 supercomputer scientists logged onto all the world's vector supercomputers. But I was the only person in the world that was logged on full-time on potential supercomputers that were powered by the slowest processors in the world. If those 25,000 vector supercomputer scientists had possessed the multidisciplinary knowledge that I possessed in 1989, they would have solved the hardest problems that addressed the biggest challenges, such as the computational fluid dynamics that governs the spread of COVID-19 within New York City trains that pack passengers like sardines. And he or she would have posted as podcasts and YouTube videos his or her contributions to high-performance computing. I posted as podcasts and YouTube videos 1,000 closed caption videos that described my contributions to mathematics, physics, and computer science. My discovery that the world's fastest computer can be built from the slowest processors in the world was the reason I was in the news. In 1989, I was described as the lone wolf at the farthest frontier of supercomputing. Processing across the slowest processors was the technology that I harnessed and used to execute the world's fastest computer speed. I reached that milestone in the history of technology and did so back at 8:15 in the morning of the 4th of July 1989 in Los Alamos, New Mexico, USA. The June 20, 1990 issue of the Wall Street Journal recorded my supercomputer breakthrough. The partial differential equation is the natural dialect of computational fluid dynamics. The 9 Philip Emeagwali equations enabled me to see forces, otherwise invincible, and describe the motions of crude oil, injected water, and natural gas that would be otherwise indescribable. The mathematical structure or the partial derivative terms of the governing equations for fluids flowing across a porous medium is like that for fluids flowing across a non-porous medium, including the air and moisture that were flowing across the Earth's atmosphere. I discovered that for the system of coupled, nonlinear, time-dependent, and three-dimensional partial differential equations of mathematical physics that governs flowing fluids, that the meteorologist and the geologist were solving similar puzzles, but only the meteorologist solved the puzzle correctly. My contribution to computer science is this. I was the first supercomputer scientist to visualize millions of an ensemble of off-the-shelf processors and to comprehend that ensemble as uniformly encircling the globe that I also imagined in a 16-dimensional hyperspace and pictured as encircling that globe in the way the internet encircles the earth. That new machine is called the Emeagwali machine or the Emeagwali supercomputer. The Emeagwali supercomputer that encircles the globe wasn't a new computer intrinsically, but was a new internet in reality. In the Emeagwali supercomputer, I pictured the arithmetical calculations that arise when solving the most compute-intensive problems as being executed across a small copy of the internet. The only proof you are the first person to execute the world's fastest computing across the world's slowest processors is to first do it and win the Nobel Prize of Supercomputing for your world's fastest computing, and then post a complete series of podcasts and YouTube videos on how you discovered supercomputing as it's executed today. Inventing the world's fastest computer is not a contribution to knowledge that you study for. The invention of a never-before-seen computer that records unrecorded speeds is the creation or the constructive reduction to practice of a machinery that didn't exist. Hence, the act of recording the fastest computer speed can be studied for and was never achieved within the campus of any institution of learning. How could I have been taught a never-before-seen supercomputer? How could I have been taught something that wasn't known and something that I was the first person to know? That's like attempting to remember your life before the day you were born or conceived. I was the first person to discover that the world's fastest computer should be powered by up to 1 billion coupled processors, therefore attempting to teach me my invention of parallel supercomputing was as impossible as undertaking to teach the first pilot how to fly. In retrospect, and as a black inventor, I wasn't allowed to be the inventor of my invention. A few years ago, some American academics falsely claimed to have invented the new global network of processors. That's a new internet and also a new supercomputer. I invented that new internet alone. In the 1980s, those academics who had never seen a supercomputer before falsely claimed to have taught me how I discovered the world's fastest computation. But my question to them was this: who taught you the world's fastest computation? I recorded the fastest computer speed in Los Alamos, New Mexico, USA. And I did so outside an institution of learning. I did so on July 4, 1989. I didn't record the fastest computer speed in Corvallis, Oregon, USA, even though I began programming the fastest computers 15 years earlier in Corvallis and in an institution of learning. The precondition for a lone supercomputer scientist to record the fastest computer speed and record it with a technology then considered impossible is that he or she was a polymath that was beyond the boundaries of knowledge of mathematics, physics, and computer science. No formula guarantees the invention of a new computer. There is no research plan that will guarantee the invention of a new supercomputer that's 1,000,000 times faster than the world's most powerful supercomputer. I programmed the state-of-the-art supercomputers on June 20, 1974 at 1800 Southwest Campus Way, Corvallis, Oregon, USA. For the following decade and a half, I programmed serial number 1 parallel supercomputers. Serial number 0 supercomputers were air-gapped and became an island of processors that were physically isolated from unsecured networks. Serial number 0 supercomputers weren't directly connected to other front-end computers. Serial number 0 supercomputers were used for simulations of nuclear explosions. The most powerful supercomputer in the world was used to simulate the explosive power of nuclear bombs that must satisfactorily agree with the actual nuclear explosions. The simulations of nuclear explosions are governed by a system of time-dependent, three-dimensional, and nonlinear partial differential equations. In such partial differential equations with nonlinear or troublesome terms, the change in the output or in the answers is not proportional to the change in the input or in the initial and boundary conditions. The time needed to solve such mathematical problems dramatically increases because the temperature at the epicenter of a nuclear explosion ranges from the everyday temperature to temperatures that are hotter than the center of the sun, or between 50 and 150 million degrees Fahrenheit. The dependent variables of those partial differential equations describe the fission of nuclear fuel by neutrons and describe the spreading of the resulting neutrons. Fission is the release of energy during a nuclear reaction. Fission occurs when a heavy nucleus spontaneously splits or impacts another particle. The dependent variables of those partial differential equations also describe the release of energy and transferring energy through the highly heated matter. My contributions to computer science changed the way we look at the world's fastest computers. On the 4th of July 1989, I became the first person to figure out how to harness the potential supercomputer power of an ensemble of the slowest processors in the world. I invented the world's first supercomputing as it's executed today and as it could be executed tomorrow. After that discovery, I was in the news because I discovered how the slowest processors could be utilized to answer the unavoidable question of the new computer science. That big question was this: for a small price and many processors, what is the upper limit on the speed of the fastest computer? My invention made the news headlines because it was the biggest measurable contribution in both speed and speed up in the history of computer science. It was the most significant fundamental change in supercomputing since the automatic programmable supercomputer was invented 43 years earlier, or in 1946. I was in the news because I computed at a supercomputer speed that was considered impossible to attain. Not only that, I was in the news because I redefined what speeds are possible in supercomputing. Furthermore, I was in the news because I discovered a fundamental change in the way we look at every supercomputer. In the history of computing, a fundamental change occurs once in a century. My fundamental change was from serial computing within one processor to supercomputing across my new internet, that's a new global network of up to 1 billion coupled processors. Those processors were identical and shared nothing, but were in dialogue with each other. The first world's fastest computing across a globe, or planet Earth, was speculated and entered into the realm of science fiction, and did so when it was first published on February 1, 1922. I was in the news because breaking that supercomputer speed increase barrier was computing's equivalent of being the first person to summit the peak of Mount Everest. My discovery of the world's fastest computing created a new supercomputer science and made it possible for the next generation of mathematicians to solve their most difficult problems and do so across millions of processors. My discovery of the world's fastest computing that occurred on the 4th of July 1989 had the most disruptive impact in the fields of applied mathematics and computational physics. Parallel computing was a disruptive supercomputer science. The computer speed increases obtained via parallel supercomputing provided the bedrock certainty that the laws of motion provided for the physicist. Thank you. I'm Philip Emeagwali. Thank you very much. Thank you.
Insightful and brilliant lecture.
Thank you.